The next model for computing quantity for inventory is for the production facilities and production firms, those that do not only rely on importing, getting from the suppliers or from other third-party manufacturing. So suppose that this is the firm that they produce the product themselves and they want to put the excess in the inventory because most often the capacity to produce exceeds the usage or the demand in the market. So this model is called the economic production quantity. Production generally happens in batches. So batch mode is widely used. That's a set of similar product that they're produced in a batch of product. So as we learned earlier, in many instances, the capacity of manufacturing to produce is more than the demand in the market. So it's inevitable to have the inventory, to put the product in inventory. For this model, there are certain assumptions that are made to be able to use the model. One is similar to the previous model, only one item or one product is actually studied here. So only one product is involved, and we assume that annual demand is known. So we assume that we have made a forecast for the demand, and that is what it is. Okay, this is an unrealistic assumption. We don't really know the demand, but we can make a forecast for it. Next assumption is that the usage rate is constant. This is also a big assumption. So we assume that the usage rate in the market, the demand, does not vary, and it's a constant. Next assumption is that the usage occurs continually, but production occurs periodically. So we assume that, for example, every day there is a constant rate of usage and demand from the market. There is a constant demand that you need to supply every day. On the other hand, you don't need to manufacture or run your production every day. You can run it periodically after you produce, because the capacity that you can actually produce is much more than the demand, daily demand. So what's going to happen is you're going to run the manufacturing, you're going to make product in a periodic basis, and then you're going to put it in inventory, and then you're going to supply the market. On the other hand, when your inventory is going to run out, you're going to start production again, and this cycle is going to go on and on. So the usage occurs continually, but the production occurs periodically. The next assumption is that the production rate is constant. We assume the manufacturing, they can produce at a constant rate. This is not a huge assumption. Another assumption is that the lead time does not vary. So when you want to start a production, or you decide to produce, that's going to be you start a production. That's going to be the lead time between the time that you want to start a production, or that's going to be similar for every cycle. So the lead time does not vary, that you put it in inventory as well. And the last assumption is, main assumption, is that there are no quantity discounts here. So we're going to actually talk about quantity discount models later as a different model. So if a bulk or a larger quantity from the demand from the market does not constitute a reduction in price or discount. All right, so now having this assumption, we can study the model. This graph shows the cycle time for production and usage. So there is these two axes here. We have the time is in the horizontal axis or x-axis, and the quantity of production or the quantity that it is in the inventory, that's on the y-axis or the vertical axis here. So let's start from the very beginning of the time here. So we start the production, and this is where we start the production up to here, this point. This that is shown by lighter color here, this area. So this is when we start production and we produce up to this point, But we also have at the same time, every day that we produce, we have constant rate of usage. So this area shows, this timeline shows the production and usage both. Production and usage both. So what happens is you produce and you also supply to the market. And if you don't consider the usage, or if you want to actually see how much you produce, is that QP. So you produce QP here. If there was no consumption, the level that you put the inventory would be QP here. But because there is a usage, a constant usage, that's why the maximum level of inventory is going to be Imax. I stands for inventory level. So the maximum level of inventory is Imax. But because there is actually constant usage, it wouldn't reach the QP level. But you produce many QP products. At this point in time, you stop production. And from here to here, which is shown by a darker color here, this area, this is usage only, as you see here. This is usage only. So when you reach the maximum of inventory, Imax, you stop the production, but the usage is going to continue daily basis until you reach this point right here. At this point, you are going to run out of inventory. So you start the production again. And this cycle run on and on again. So this is going to be a runtime. You have production and usage. You stop production here, and you're going to have consumption only here. And then again, you start production here, and this cycle goes on and on and on. So this is the cycle time that you see that is going to be repeated here, and it's here, and also it's here. Okay. This cycle time contains two periods. One is the runtime period here. This runtime, which is shown here, this runtime that you have production, and also you have actually consumption as well. But you have production, so this is the runtime. And there is this period that you only have usage. So this period right here, and also this period right here, you only have usage. You have a stopped production, you don't produce, you only use from the inventory. Okay. So now that we know about these cycle times, production time and usage time and runtime, let's go ahead and study the model. So here is the model. The logic is the same as the previous model. We want to find the optimal quantity, production quantity, or QP here. So let's see how this works. So the logic is we want to find QP such that it would minimize the total cost of the inventory. The total cost of inventory, since this is a manufacturing and not actually they don't order from outside, so there is no order cost here. There's no order cost. But there is a setup cost for running the running period when you want to start the production and manufacturing. There is a setup cost associated with that runtime. So instead of order cost here, we have another component, the setup cost. So we're gonna write the formula for the total cost of inventory. The total cost of the inventory, which we want to minimize it to find the optimal quantity of production, that's going to be carrying cost, the cost associated with carrying and holding inventory, plus the setup cost. So setup cost is each time that you start running, it's going to cost us money. The carrying cost is similar to what we had for the previous model. So the carrying cost is we want to see for example, for each day and for how much you have left in the inventory, that's going to cost you money, right? So instead of going daily basis, we're going to use the average. So the average for the inventory level is I max at the beginning. So that's I max as the maximum inventory level. And we have another period which is the inventory level is 0. So the average of these two is I max divided by 2. So this is the average level of inventory. We're going to multiply the average level by H, which is the holding cost or carrying cost per unit. This is going to give us, this multiplication is going to give us the carrying cost. Okay, so that's the carrying cost. Now let's focus on the other component of the cost, which is setup cost. So setup cost, assume that S stands for setup cost per run. Each time that you want to run the production is going to cost S whatever, how much S is. So what you need to do here is to multiply the time that you would need to run in a yearly basis. How would you compute that? Well, you can actually make a forecast for your demand. We assume one of the assumptions for this model is that the demand is known. Demand is known, so we know what D is. Also, we know how much we can actually produce. This is Q. Q actually here is a variable. So based on this, D divided by how much you produce each time, that's Q. That's going to give you how many times you need to run the production. Okay, so for example, if the demand is 10,000 and each time that you run, you produce Q equal to 1,000 items, 1,000 products, then you need to run 10 times. Okay, so D divided by Q would be 10, and other for other numbers as well. So this is how you can find the setup cost. The number of time that you want to run the production multiplied by the setup cost per run, which is S. All right, so let's see in this formula, what do we know and what they are. Imax is the maximum level of inventory. How we can compute that? Well, you know how much you produce, that's Q. It's variable, you can decide how much you want to run, how much you want to produce based on how many days you run. And this is the variable that we want to find the optimal value for that. So this is the optimal value for that is here, which as you see here, it has two components here, or two multiplication components here. The first one is the square root of 2 multiplied by D multiplied by S divided by H, which is kind of similar to what we had for the previous model, except for here we had the setup time cost, the S, previously we had the order cost. Okay, and this is actually multiplied by another component, which is a square root of P divided by P minus U. P is the production rate. If you remember from the assumptions, we assume that the production rate is constant, and U here is the usage rate, and we assume that that's also constant. So P and U are just numbers. These are parameters. So if you multiply these together, you're gonna get the optimal quantity for production, QP. All right, so let's go back to talk about Imax. How do you find Imax? Well, this is the formula for Imax. After you find the quantity, production quantity, the optimal quantity using this formula, Imax is equal to the optimal quantity QP divided by the production rate multiplied by P minus U. Or you can write it as this one. The optimal quantity production QP multiplied by 1 minus U over P. U is the usage rate and P is the production rate. This means that the maximum level that you would have in the inventory depends on the quantity that you produce and the production rate and the usage rate. So these three components are going to dictate how much inventory you would have. Fine. There are other formulas on this right section that you see here. Cycle time is the time that, if you remember, the time that you have usage rate, production rate, and usage rate, and also only usage rate. So that's the cycle time that is going to be repeated. So if you remember from the previous slide, this is time and this is quantity, and we have production, this is Imax, and this period right here, this period is runtime, and this period is the cycle time. So cycle time, this cycle time, the formula for cycle time is the quantity that you produce, QP, that we compute here, divided by usage rate. Quantity that we produce divided by usage rate. We can also compute the runtime. So the runtime is the time period that you only have production, and that's going to be the quantity that you want to produce divided by P, which is the production rate. That's going to give you how many days, for example, you need to run to produce QP. Imax is, as we found it here, that's QP, Q divided by P multiplied by P minus U. If you use the QP here, that's going to give you the maximum inventory level at optimality. And the average of I, the inventory average level, is just Imax plus 0 divided by 2, or Imax divided by 2, maximum inventory level divided by 2. So this is going to give us these components. So let's now see an example. A toy manufacturer uses 48,000 rubber wheels per year for its popular dump truck series. The firm makes its own wheels, which it can produce at a rate of 800 per day. So 48,000 rubber wheels per year, and the production rate is 800 per day. The toy trucks are assembled uniformly over the entire year. Carrying cost is $1 per wheel a year. Setup cost for a production run of wheels is $45. The firm operates 240 days a year. Determine the following. A. Optimal run size. That's the QP production quantity at optimality. So what is QP? Run size. B. Minimum total annual cost for carrying and setup. So that's the total cost, minimum total cost. C. Cycle time for the optimal run size. So if you produce at QP level size, what would be the cycle length, the cycle time length? D is the run time. How many days you would have to run at if you want to produce at QP. So please pause, work on this problem, try to solve it. After you're done, come back to see the solution. Let's solve this problem. So what do we have here? We have a toy manufacturing that uses 48,000 rubbers per year. So that's their demand. The demand here, the yearly demand is 48,000 of rubber wheels. Right. So since this is a manufacturing company, so they produce rubber wheels and they have daily usage, and they put the excess into the inventory. So this is going to be our second model, the model that we studied, the production economic model, economic production model. So that's what we're going to use here. So the demand, the yearly demand is 48,000 rubber wheels. What else do we know? We know that the production rate for this company, the manufacturing company, is 800 per day. So P, the production rate, is 800. What else do we know? We know that the carrying cost is $1 per wheel per year. So that's H. H is $1 per unit per year. And the setup cost per run is $45. So S is here is $45. That means that each time they start production, it's going to cost $45. And we also know that the company works for 240 days a year. All right. What do we need to compute first? We need to compute the usage rate, U, the usage rate. So what is U? We know that the demand is 48,000 a year. So to compute the U, the usage rate per day, that would be how many units they use per day. If they need 48,000 a year, which is 240 days, that means they would need 48 divided by 48,000 divided by 240 days that they work per year to compute the daily usage rate. So that would be 200. So U, the usage rate is 200. I'm going to write it right here. U is 200. The first part of the question asks for the optimal production quantity, or QP. It says what is the optimal run size. Run size is actually the production quantity at optimality. QP, what is QP? Optimal production size each time you run. So we have the formula. We're going to use the formula. The formula is the square root of 2 multiplied by D multiplied by S divided by H multiplied by the second component, which is the production rate, P, divided by P minus U, the production rate minus the usage rate. So if we plug in the numbers here, this is what we're going to get. We're going to get 2 multiplied by demand, which is 48,000, multiplied by S, which is 45, divided by H, which is 1, multiplied by P, which is 800, divided by 800 minus 200. So if we do this math, we're going to get QP equal to 2400. 2400. So each time they run, they do the manufacturing, they're going to produce, if they produce 2400 units, rubber wheels, that's going to make the total cost, the inventory cost, minimal. So that's going to be the optimal production level. So let me write this, clean this up and write it. Part B of the question asks for the total the minimum total cost for carrying and setup cost of the inventory if we produce at optimal quantity, which is 2400 that we computed here. So we need to compute the total cost of the inventory at minimum cost, which is going to be at optimality. So the total cost, as we know from the formula, that's I max divided by 2 multiplied by h. So this component gives us the carrying cost, annual carrying cost. The second component is going to give us the setup cost of running, the setup cost. So that would be D divided by QP multiplied by S. So we have everything except for Imax. We need to compute Imax. Let's compute Imax. Imax, according to the formula, is equal to QP multiplied by 1 minus U divided by P. So that's 2400 multiplied by 1 minus 200 divided by 400. And if you do the math, you're going to get Imax equal to 1800. Let me clear this up. I'm going to put Imax here as 1800. So 1800 divided by 2 multiplied by h plus h is 1, d is 48,000, qp is 2400, and s is 45. If you do the math, this is going to be 1800 divided by 2 multiplied by 1, so that's $900, plus the second part also would be $900. So that's a total of $1,800, $1,000 and $800. So that's the total cost at minimum. Let me clear this up and write it here. Now let's go to part C. So part C is asking for cycle time if we produce at optimal quantity QP. According to the formula that we have, cycle time, I'm going to write it as CT, cycle time. Cycle time is equal to the optimal quantity of production QP divided by the usage rate, U. So if you plug in these numbers, QP is 2400 and U is 200. So the cycle time is 12 days. That means that every 12 days we are going to have a start production. So these 12 days includes the runtime day, the run period, which we do the production, and there is some part of it, there is no production, we have a stop production, and there is only going to be usage. All right, let's go to the part D, last part in the question. So last part in the question, there is asked for the runtime. So let's see what is runtime. Let's compute runtime. Runtime is the time period, the length of the time period that we do the production. For how many days we do the production. So according to the formula, the runtime equal to QP divided by P. So that's the optimal quantity of production divided by U, the production rate. We produce 2400 each time, and the production rate is 800 per day. So how many days, if we produce at 800 per day, how many days we need to produce to make 2400? So that's 2400 divided by 800, that's 3 days. So the runtime is 3 days. So out of the 12 days cycle time, we start production and we do the production for a period of 3 days, and for the rest, which is 9 days, we don't produce. Again, after the 12 days, we're going to start producing. We're going to produce for 3 days, and after that, we're going to stop. And after 12 days, we're going to continue. So this cycle is going to go on and on. All right, so this is just a neat and clear illustration of the solution. So we know that the demand is $48,000, 48,000 wheels per year. That's the demand per year. The holding cost is $1 per wheel per year. The setup cost is $45 per run, each time that you run. The production rate per day is 800. The usage rate is, as we computed, is 200 wheels per day. So the optimal quantity to produce to make the total cost of the inventory minimum, we need to produce at 2400 product or the rubber wheels per run. So if each time that we do the manufacturing, we produce 2400 rubber wheels, we're gonna make the total cost minimum. And the part B, the total cost of the inventory, which is carrying cost and the setup cost, that's going to be $1,800 as we computed. So for that, we computed IMAX, the maximum level of inventory, using this formula, and that was 1,800. So the maximum level of inventory, if we produce 2,400, it's going to be 1,800. That's the maximum level of the inventory. Cycle time, the formula for cycle time is QP divided by U, the usage rate. So that's 2,400 divided by 200, that's 12 days. So we need to start production every 12 days. Or every 12 days, we have to start running the manufacturing part. The runtime for the time period in which we do the manufacturing or we're running the machines, that's going to be QP divided by P, 2,400 divided by 800, that's 3 days. So out of these 12 days cycle that we make production, that we actually have the cycle time, 3 days of it we manufacture and 9 days of it we don't manufacture.